So I'm going to give you the summary of the PicSat mission. So the PicSat mission is an astronomical mission, which was first discussed in 2014 during a conference on the star Beta Pictoris. Beta Pictoris is a very interesting star for astronomers because it's very young, very bright. It's, you can see it by eye if you're in the south hemisphere. And it's interesting for astronomers because it's very young, and there's already still the disk, the debris disk on the star, as you can see here on these images. If you use the Hubble Space Telescope, you will see something like that. So that's the light scattering of the scattering of the light from the star, the scattering from the dust inside the disk, and you see this hadron system. So the system is exactly at 90 degrees. So in your direction of in the way you see the star, in the direction you see the star. So you see it as an horizontal disk. And if you look at this image closely, then you see that there's a secondary disk, which is slightly tilted with respect to the first one. And this secondary disk was, at the time, it was around 2006, signed, astronomers thought it was signs of the presence of the planet. So this planet was later discovered by Anne-Marie Lagrange in 2009, beginning of 2009. Looking at data from Beta Pictoris of 2003. So it's a red dot to the upper left. And in end of 2009, 2010, it was observed again on the other side of the star. So here the star is blocked, it's inside in the middle, and the 2 points are the position of the planet at 2 different levels. So it was images in 2010, but then with time, astronomers kept observing the planet as it orbits around the star. And you can see the different position here. And from this position, they can deduce of course, the orbit of the planet around the star. They can predict the moment where the planet will be between us and the star. So it will be transiting in front of the star. An astronomer wants to catch this transit because it will give us information with respect to the size, density, the structure of the planet. The orbital parameters are not very well known. They are around 18 years, so it happens each 18 years. And the predicted orbit was between 2017 and 2018. So at the time of the conference, which was 2014, we thought about the idea to build a satellite to observe this transit. So that's the time sequence for building the PicSat satellite. So in 2014, we got the idea, we got the money, and then everything started from that. In 2000, so that was 2014. In 2015, we did the first design phase. So we got the money and we started the design. There was several technology challenge to be resolved to be able to observe the planet as it transits in front of the star. The first one is to have high accuracy photometry, and to do that you have to get rid of all the stray light coming from the moon, the Earth, or other stars. So the solution for a big space mission like Kourou is to use the baffle. But we couldn't do that inside the CubeSat, so we decided to use a single notch fiber instead of the backbone. The second technology we wanted to develop was to use a single avalanche photodiode. So they are used for quantum measurement, and they have zero noise, and each photon is individually measured this way. And this way we can have high temporal and high sensitivity for the detector. So it's an Peltier system, so we can thermally regulate it. And the third problem was the fine pointing. So we decided to buy the ADCS from Hyperion Technology. But even with the ADCS from Hyperion, we couldn't reach the sensitivity. We wanted to have 1 arc second pointing, and the Hyperion spec were 30 arc-second pointing. So we need a second stage fine pointing system. So we came up with this idea to have an off-axis parabola and the fiber mounted on a piezo stage, an XY piezo stage. And we use the piezo stage to center the position of the star on the top of the fiber. We do high frequency modulation, around 100 or 200 hertz. And by this fast modulation, we can know where is the star and close loop the position of the piezo using the flux observed with a single avalanche photodiodes. So we did some first, so in 2015 we did the first campaign of tests, including thermal vacuum or vibration tests. So at this time we brought the piezo, which was an off-the-shelf piezo from PI, Physical Instruments, and we decided to go for a different piezo. And in 2016 we had the final design with the new piezo from Cedra Technology, so a piezo which was conceived to fly in this mission, and it has it's based on the same type of piezo that was used on the Rosetta mission, and the star tracker that we moved from the ADCS position up to the front of the CubeSat. So here you have the star tracker at the bottom left, and next to the star tracker you have the payload with the off-axis camera and the single mode fiber, which is on the piezo, which is on the orange one. So 2015 was designed, 2016 all the design was done and all the components were there. We did the call for bid to have all the different components, so it took lots of time. And then we did the first qualification test of the different device, including breaking mirror or testing the star tracker on sky and doing as many tests as we could do to ensure that it would work. So we done that during the full year of 2016. And end of 2016, we had a final review to decide if we are going to buy the launch on it. And we decided to go for it. So in 2016, we bought the launch, which was scheduled for end of 2017. So in 2017, we realized that we had lots and lots and lots of software to do, including the ground segment. And that was a hard part. We hired additional people, but 2017 was software. So first there's the onboard computer software. So we use a special framework which is called Jericos with FreeRTOS. But the onboard computer is one thing. We will think about that very early in the process. Then there's all the ground segments, which is okay. You know that you need an antenna, but it's not just an antenna. You need the full software to be able to talk with the satellite, to store the data, and to know what's happening up there. And that's lots of software. And when you think about that software, you think about the last piece, which is missing that you didn't think about it before, is the communication protocol. And the full communication protocol, that's very complicated. And you better think about it very early in your mission, because this communication protocol affects both the onboard computer, the ground segment, but also the database, and how you store, you plot the data, and all the telemetry. So that's just, don't forget the software and the communication. So that's for most of 2017. And end of 2017, we did the final assembly of the satellite. We have it here. So for the full satellite, the platform was built by IPSIS, and we had a deployable solar panel. And that was it for 2017. No, last thing. We bring it to Delft to ISIS, so they ship it to India. So the flight, sorry, I had a video, but it didn't go through the PDF. But you're supposed to see a nice video of a rocket like so that was very impressive. And a few hours later, we got the first communication with the satellite. So that was big. But here are a few consequences. There are a few main points that we got from this mission. First is we were the first one to know that the satellite was alive, but just by 20 minutes. Because 20 minutes later, there was another radio amateur who got the signal. And during the full mission, lots of radio amateur people, the full radio amateur community, followed our project a lot. So it comes from the fact that the frequency that we used for communication is using the amateur radio band. So very early in the process, we got into contact with the International Radio Amateur Union, and we managed to get their frequency, which is not something they do often, but we could do it because we had some kind of scientific pedagogical project, and also because we put a transponder inside our satellite. So the radio amateur could actually talk to the satellite and talk to each other using the satellite. But it's not just about using a transponder. All the radio amateurs, they like to listen to the satellite. So we use them to get the telemetry of it. So the orbit of PicSat is a sun-synchronous orbit at 505 kilometers. So it rotates around the Earth in 90 minutes. We have two or three passengers of the satellite above our ground station in Madras. But using all the radio amateur community, we got almost 24 contact with the satellite. We set up a protocol for them to upload the data to our website and to put the data inside our database and plot in real time what they did upload. So they could see there was a chart with the number of packets they upload, who was the one who uploads the most packets. It was very, very efficient. And we use Twitter a lot. And if you can have radio amateur wavelengths, you should be encouraged to use them, because if you play the game, they are very strong and active community. Then the second result is that the ADCS was not working. So the data link worked perfectly, so we were very happy with that. But when we started the pointing system, then the reaction wheel didn't follow the target. So the reaction wheel rotation is at the bottom, and the target are the small cross here. And there were issues with the communication inside the ADCS. So we could never get a quaternion. So the star tracker wasn't able to give us the reference. So that was the problem with the ADCS. But the payload, on the other hand, worked well from what we know, because since the ADCS didn't manage to point the star, we couldn't really get photometry in the star. But most of the part of the payload, like the gyro system or the thermal regulation, was working. So that's during 10 weeks, we tried to fix the ADCS system. But after 10 weeks, on March 20th, we got this tweet from a radio amateur in New York, who told us that there was no more signal from the PicSat satellite. So following this tweet, we tried to observe it, but we couldn't hear anything. And that's the last beacon that we got from the satellite during the last 16 hours. And you can see, so each one of the name here, top and bottom, are the name of a radio amateur who got a data set from the satellite. And the small dot on the map are actually the position of the satellite when it emitted the beacon. And you can see it passing across Europe, over Europe, and going through down to Brazil one time, then going back to Japan, and then going back again to Brazil, and then from that we couldn't hear anything anymore. It was around 13 UT time, and like 10-15 minutes later it should have been across Indonesia, and nobody heard it in Indonesia. And nobody heard it anymore ever. So even with big radio, okay, so since we have the help of the radio amateur, like they have this huge antenna, like 25 meters antenna. Everybody tried to listen to the satellites. We know it's still there, but we know also there's no emission. So there's different theories that are fighting each other. I'm limited to my time, but just I suppose you want to know, I want to skip that. So that's the last telemetry from the last months. So everything's nominal. We have a few reboots. One reboot of the system, it's 3 days, but everything was fine. Temperature was fine, communication was fine, so there's no sign from the telemetry of any aging of the components. From the TLE, we got some kind of event which is linked to some kind of high solar wind during the last 24 hours. So when there's lots of solar winds, the atmosphere puffs up, and then the satellite goes slow down, and you can see that on the TLE, the 2 lines elements. So there was high solar activity at this time. Here it's a geomagnetic activity, which is also linked to the solar activity with a huge spike 20 hours before we lost control of the satellite. And we link that to a high concentration of electrons in the Van Allen pairs. Usually they are at 3 or 4 higher position, but along the pole they can go low. So that's one of the explanations we can have of this. We also have software ideas. That's
Any questions?
Thanks for this talk. So what are the lessons learned that you could give us for the future?
First, buy 2 satellites. And then, when the first one failed, you just send the other one. So that's the main lesson. Because like an event like that, we don't know if it's random or not. We found some error in the software too. So we would have fixed the error in the software and send it again. We think maybe it's a combination between activity and bug in the software, which could cause some kind of boot loop in the software. So we would have fixed the software and launched it again. But we don't have a second, so buy a second one. And the second, for the ADCS, buy an ADCS which works. But the problem is it's very hard to test. We did a full setup to test the ADCS, but it's very hard to test on the ground. So buy an ADCS which has already fly. So this way you're sure that it works.
Any further questions?